This will be our second lesson about the integral test for infinite series. So in this lesson, we're going to talk about how to test if a series diverges by comparing it to an integral. And so the type of series that we'll look at in this video are of this form. So they're the sum from n equals 1 to infinity of f of n, where this f is a positive decreasing function of x. A good example to have in mind is f of x equals 1 over x, in which case the series that we'd be looking at is this one, sum from 1 to infinity of 1 over n. And what we'll want to do is try to test if this series diverges, and we'll do it by comparing it to an integral of this function f. So, in this video, we're going to derive an inequality, and this inequality takes this form. So, on the left-hand side, we have the nth partial sum of this series. So we pick some number capital N, and we just sum the series from 1 to capital N and stop there. And on the right-hand side, you see the integral from 1 to capital N plus 1 of this function f. And this inequality says that the left-hand side is greater than or equal to the right-hand side. And what we can learn from it is that if the integral diverges as n goes to infinity, so if the integral diverges as n goes to infinity, then so does the series. So that's the use of this integral test. Now in the rest of this lesson we're going to derive this inequality. So the way we'll derive it is based on studying the plot of this function f of x. So we're going to draw it. So here we draw this function f of x, and we've drawn it decreasing since it's a decreasing function. And we're interested in the part of f of x between lowercase n and lowercase n plus 1. And we're going to draw the same picture twice because we're going to compare two different areas associated with this graph. So on the left-hand side, we'll look at the total area under this curve between n and n plus 1. So this blue region shown here. And we can calculate the area of this region using an integral. It's just equal to the integral from n to n plus 1 of f of x. On the right-hand side, we're going to instead look at a rectangle that starts here at f of n. So we're going to look at the rectangle that starts at f of n and stretches between n and n plus 1. So that's this red region here. And we can calculate its area too. It's just equal to the base, which has length 1, times the height, which is f of n. So it's just equal to f of n. Now, by comparing these two pictures, you can clearly see that f of n, which is equal to the area of the rectangle on the right-hand side, is greater than or equal to this integral. And this integral is equal to the region shaded on the left-hand side. So this will be the key inequality that we'll use to derive the integral test. So the last step of the lesson is just to use this inequality to derive our formula for the nth partial sum. So to do it, let's write out the partial sum again. And now what we'll do is just use this inequality on f of n here. So we have that this sum is greater than or equal to the sum from 1 to capital N of the integral from n to n plus 1 of f of x. And now what we have here is a sum of these integrals. They go the integral from 1 to 2, then from 3 to 4, and so on, all the way up to capital N plus 1. So if we evaluate this sum that appears here, we find that it's actually equal to the integral from 1 to capital N plus 1 of this function, f of x. And that's the final step that's needed to derive the inequality that we use in the integral test. So, putting this all together, we find that this partial sum of our series is greater than or equal to the integral from 1 to capital N plus 1 of f of x. And so we learn from this formula that if this integral diverges as n goes to infinity, then so does the series. And that completes this lesson.